Imagine boarding a plane in New York and landing in London 90 minutes later. Or flying from Los Angeles to Tokyo in under 3 hours. This isn't science fiction anymore. It's the promise of hypersonic travel. And we're closer than you might think. Welcome back to the channel. Today we're diving deep into one of the most exciting frontiers in aerospace. The race to achieve practical hypersonic flight at speeds exceeding Mach 5. That's over 3,800 miles per hour. We're going to explore the cutting-edge technology making this possible, the massive engineering challenges that still need solving, and whether hypersonic passenger travel will actually become a reality in our lifetimes. From Boom Supersonic's ambitious Overture airliner to the mysterious SR-72 son of Blackbird, from NASA's groundbreaking X-plane research to the fundamental problems of heat, materials, and sonic booms, we're covering it all. So buckle up, because we're about to go hypersonic. Section 1. What is hypersonic flight? Before we dive into the specific aircraft and technology, let's establish what we're actually talking about. In aerospace, we measure speed in Mach numbers. Mach 1 is the speed of sound, roughly 767 miles per hour at sea level. Commercial airliners cruise around Mach 0.85. The legendary Concorde flew at Mach 2. Hypersonic flight begins at Mach 5 and above. At this speed, you're traveling at approximately 1 mile per second. The physics of flight changes fundamentally at these velocities. Why does Mach 5 matter? It's not just an arbitrary number. At Mach 5, several critical things happen. The air around your vehicle becomes so compressed and heated that it starts behaving more like a fluid than a gas. Shock waves become incredibly intense. And most importantly, the heat generated becomes extreme. We're talking temperatures that can melt steel. This is what engineers call the heat barrier, and it's the primary reason hypersonic flight has remained so elusive for commercial aviation. A brief history. Humans first achieved hypersonic flight in 1949 with the bumper rocket. In the 1960s, the X-15 research aircraft reached Mach 6.7 with a pilot on board, a record for crewed, powered aircraft that still stands today. But here's the key difference. Those were rocket-powered research vehicles designed for brief flights. What we're talking about now is sustained, practical hypersonic flight using air-breathing engines. In 2004, NASA's X-43A Scramjet reached Mach 9.6, proving that air-breathing hypersonic propulsion was possible. But that vehicle flew for only about 10 seconds before gliding to a crash landing in the ocean. The challenge now is making hypersonic flight sustainable, controllable, and eventually safe enough for passengers. Section 2. The key players. Boom Supersonic. The pragmatic approach. Let's start with the company that's probably closest to putting passengers in a high-speed aircraft, Boom Supersonic. Now, full disclosure, Boom isn't actually building a hypersonic aircraft. Their Overture is designed for Mach 1.7, which is supersonic, not hypersonic. But they're included here because they're tackling many of the same fundamental challenges, and their approach tells us a lot about what's realistic. In January 2025, Boom's XB-1 demonstrator broke the sound barrier, becoming the first independently developed supersonic jet to do so since Concorde retired in 2003. This wasn't just a publicity stunt. It validated their aerodynamic design, materials, and control systems. The full-scale Overture is planned to carry 64 to 80 passengers at twice the speed of current airliners. They've secured orders and pre-orders for 130 aircraft from United, American, and Japan Airlines. Their factory in North Carolina is already built, and they're developing their own Symphony engine. Why mention them in a hypersonic video? Because Boom is demonstrating what it actually takes to bring high-speed flight to market. Certification, manufacturing, airline partnerships, and a viable business model. If they succeed at Mach 1.7, That's still a massive achievement and could pave the way for even faster aircraft. Importantly, in June 2025, the Trump administration lifted the 52-year ban on supersonic flight over land in the United States. This dramatically expands the potential market for supersonic and future hypersonic aircraft. The SR-72, mystery and military might. On the complete opposite end of the spectrum, we have the SR-72, nicknamed the Son of Blackbird. This is Lockheed Martin's secretive hypersonic aircraft program, developed by their legendary Skunk Works division. And when I say secretive, I mean it. Most of what we know comes from occasional hints and reports. The State Route 72 is designed to exceed Mach 5 and potentially reach Mach 10. Unlike its predecessor, the State Route 71, it will be unmanned and focused on reconnaissance and potentially strike capabilities. According to reports from 2025, a prototype could be completed by late 2025, with a possible in-service date around 2030. The aircraft is expected to be over 100 feet long and will use a revolutionary propulsion system we'll discuss shortly. The State Route 72 represents the military side of hypersonic development, where cost is less of a constraint and the focus is on speed, altitude, and survivability against advanced air defense systems. NASA's X-planes, the foundation. NASA has been the quiet pioneer of hypersonic research for decades. Their X-plane series has pushed the boundaries of what's possible. The X-15, flown in the 1960s, remains the fastest crewed aircraft at Mach 6.7. The X-43A reached Mach 9.6 in 2004 using a Scramjet engine. The X-51 Waverider achieved 210 seconds of Scramjet-powered flight at Mach 5.1 in 2013, a record at the time. Today, NASA continues hypersonic research through various programs, developing the fundamental technologies that commercial and military aircraft will eventually use. They're working on thermal protection systems, advanced materials, propulsion systems, and autonomous control algorithms. Stratolaunch, the dark horse. Here's a name you might not have heard: Stratolaunch. Their Talon-A hypersonic vehicle has been quietly making history. In December 2024 and March 2025, Talon-A became the first reusable hypersonic vehicle in the United States to fly above Mach 5 and land intact. Think about that. This thing flies faster than Mach 5, collects data, and then lands so it can fly again. Talon-A is air-launched from the massive rock carrier aircraft, the world's largest plane by wingspan. While it's currently a testbed for the military and commercial customers, it's proving that reusable hypersonic flight is achievable. These are the major players, but there are others: Hermes working on a Mach 5 passenger aircraft, Hypersonics in Australia, Venus Aerospace, and various Chinese programs we know less about. The race is global, and it's accelerating. Section 3. The technology, propulsion. Now let's get into the technical heart of hypersonic flight. How do you actually power something to go 5 times the speed of sound? The fundamental challenge. Traditional jet engines don't work at hypersonic speeds. Here's why. A regular turbojet or turbofan uses compressor blades to squeeze incoming air before mixing it with fuel and igniting it. But at hypersonic speeds, the air is already moving so fast that compressor blades can't handle it. They'd literally be torn apart. The Scramjet solution. This is where the Scramjet comes in. Scramjet stands for Supersonic Combustion Ramjet. In a Scramjet, there are no moving parts. The engine uses the vehicle's own speed to compress incoming air. The air flows through the engine at supersonic speeds. It never slows down to subsonic like in a traditional engine. Here's the process. Air enters the inlet, is compressed by carefully designed shock waves. Fuel is injected, combustion occurs at supersonic speeds, and the exhaust is expelled, creating thrust. NASA's X-43A proved this works at Mach 9.6. The X-51 demonstrated sustained scramjet flight for over 3 minutes. Stratolaunch's Talon-A is using scramjet technology for reusable flights above Mach 5. But here's the catch. Scramjets only work above about Mach 4. Below that speed, they can't generate enough compression to sustain combustion. The turbine-based combined cycle, TBCC. This is where things get really interesting, and it's the approach both the SR-72 and several other programs are taking. A TBCC engine is actually 2 engines in one. It has a traditional turbofan engine for takeoff and acceleration to supersonic speeds, and a scramjet for hypersonic flight. Here's how it works. The aircraft takes off using conventional jet engines. As it accelerates through Mach 1, 2, and 3, it's still using turbofan power. Somewhere around Mach 3 to 4, the engine transitions, bypassing the turbine and switching to scramjet mode. The scramjet then takes over for hypersonic acceleration and cruise. This is incredibly complex engineering. The engine has to seamlessly transition between 2 completely different modes of operation while traveling at thousands of miles per hour. Getting this transition smooth and reliable is one of the major challenges facing hypersonic aircraft development. Lockheed Martin is developing TBCC technology for the SR-72. Hermeus is working on their own version called Chimera. These companies are solving problems that have never been solved before. Fuel considerations. Most hypersonic test vehicles have used hydrogen fuel because it has excellent energy density and cooling properties. But hydrogen is difficult to store and handle. Some programs are exploring hydrocarbon fuels like jet fuel, which would be much more practical for commercial aviation. Boom Supersonic, for example, is designing Overture to run on sustainable aviation fuel. The fuel choice affects everything: engine design, vehicle weight, range, and operational practicality. Alternative approaches. Not everyone is going the scramjet route. Some programs use rocket engines, which work at any speed but consume enormous amounts of fuel and oxidizer. There's also research into rotating detonation engines, which use continuous detonation waves to achieve better efficiency. These are still highly experimental but show promise. The propulsion challenge isn't solved yet. We have technologies that work in test conditions, but making them reliable, efficient, and practical for operational aircraft is the next mountain to climb. Section 4. The heat problem. If propulsion is the heart of hypersonic flight, thermal management is the skeleton that holds everything together. And this might actually be the harder problem to solve. Why hypersonic flight gets so hot? When you're flying at Mach 5, you're not just moving through air, you're compressing it violently in front of you. This compression generates enormous heat through aerodynamic friction and shock waves. The leading edges of a hypersonic vehicle can reach temperatures between 3,000 and 5,000 degrees Fahrenheit. That's hot enough to melt steel, titanium, and most conventional aerospace materials. The nose cone and wing leading edges experience the most extreme heating because they're the first parts to hit the air and they're typically sharp for aerodynamic efficiency. But here's the cruel irony. The sharper and more aerodynamic you make these surfaces, the hotter they get. Blunt surfaces create a larger shock wave that pushes the heat away, but they also create much more drag. Materials science to the rescue. This is where materials science becomes absolutely critical. The X-15 in the 1960s used Inconel X, a nickel-chromium alloy, for its outer skin. It could withstand extreme temperatures while maintaining structural integrity. Modern hypersonic vehicles use even more advanced materials. Carbon-carbon composites can handle temperatures above 3,000 degrees Fahrenheit and have excellent thermal conductivity. The X-43A used these extensively. Ceramic matrix composites, or CMCs, are increasingly important. These materials combine ceramic fibers with ceramic matrices, creating something that's lightweight, extremely heat-resistant, and can maintain structural properties at temperatures where metals would fail. Ultra-high temperature ceramics, or UHTCs, include materials like hafnium carbide and zirconium carbide. These have melting points above 6,000 degrees Fahrenheit, higher than most materials on Earth. They are being researched for leading edges and nose cones. One promising material getting attention is CZROC, carbon fiber reinforced with zirconium oxycarbide. It's relatively inexpensive to manufacture, highly scalable, and can withstand the extreme conditions of hypersonic flight. Thermal protection systems. But materials alone aren't enough. You need complete thermal protection systems, or TPS. There are several approaches. Passive cooling uses insulation and radiation. The Space Shuttle used ceramic tiles that insulated the aluminum structure underneath while radiating heat back into the atmosphere. This is relatively simple but heavy. Heat sink structures absorb heat into the material itself. The X-15 used this approach. Its thick metal skin would heat up during flight and then cool down afterward. This only works for relatively short flights. Active cooling circulates a coolant through channels in the vehicle's skin. This is incredibly effective but complex. The coolant, often fuel, flows through the structure, absorbing heat before being used in the engine. This is called regenerative cooling. Transpiration cooling is a cutting-edge approach where coolant is forced through tiny pores in the material, creating a cooling layer on the surface. This is still mostly experimental but shows great promise. The SR-72 reportedly uses a combination of advanced materials and active cooling systems. The exact details remain classified, but we know thermal management is a major focus of the program. The structural challenge. Here's another problem. When materials heat up, they expand. When different parts of your aircraft are at vastly different temperatures, say, 3,000 degrees Fahrenheit on the leading edge and 70 degrees Fahrenheit in the passenger cabin, you get thermal expansion differences that create enormous stress. Materials that are in contact have to expand at compatible rates, or you'll get warping, cracking, and structural failure. This requires careful material selection and sophisticated structural design. Engineers use finite element analysis and computational fluid dynamics to model these thermal and structural loads, but there's still no substitute for actual flight testing in real conditions. The bottom line. Solving the heat problem requires advances in materials science, manufacturing techniques, and cooling systems. We're making progress. Companies like Canopy Aerospace are developing next-generation thermal protection systems, and materials research is ongoing at universities and national labs. But this remains one of the primary barriers to practical hypersonic flight. You can have the perfect engine, but if your aircraft melts or structurally fails from heat stress, you're not going anywhere. Section 5. Control and stability. There's another challenge that doesn't get as much attention but is absolutely critical. How do you control something moving at a mile per second? The speed of decision-making. At Mach 5, an aircraft covers a mile every second. In the time it takes a human pilot to perceive a problem, process it, and react, typically several seconds, the aircraft has traveled miles. This is why most hypersonic vehicles are either unmanned or will require extensive automation. The SR-72 is designed as an unmanned vehicle specifically because of this challenge. Aerodynamic instability. Hypersonic flight occurs in a regime where aerodynamics are poorly understood compared to subsonic flight. The shock waves, turbulence, and flow patterns are incredibly complex. Small control inputs can have dramatic effects. The vehicle can be incredibly sensitive to changes in angle of attack, sideslip, or control surface deflection. Get it wrong, and you could induce a spin, loss of control, or structural breakup. The X-15 program experienced what pilots called unstarts, sudden engine stalls caused by shock waves disrupting airflow. When this happened at Mach 6, It was terrifying and potentially catastrophic. Autonomous control systems. This is where artificial intelligence and advanced control systems become essential. Researchers at places like Georgia Tech and the University of Virginia are developing control algorithms that can make decisions in milliseconds. These systems use optical sensors that operate at the speed of light rather than traditional pressure sensors. They continuously monitor the engine's combustion, the vehicle's attitude, and environmental conditions, making constant tiny adjustments to maintain stable flight. Stratolaunch Talon-A has demonstrated autonomous hypersonic flight and landing. The vehicle makes all critical decisions itself, though humans monitor and can intervene if necessary. Structural coupling. Here's something really tricky. At hypersonic speeds, the vehicle's structure, its aerodynamics, its propulsion, and its thermal state are all tightly coupled. Change one, and you affect all the others. Heat changes structural stiffness, which changes aerodynamics, which changes heating rates. Throttle changes affect shock wave patterns, which affect flow into the engine, which affects thrust and heating. Managing all these interdependencies requires sophisticated simulation and real-time control systems that didn't exist until recently. Testing and validation. The challenge is that you can't fully test these systems on the ground. Hypersonic wind tunnels can simulate some conditions, but they can't replicate everything simultaneously. The heat, the structural loads, the propulsion interactions, all happening together for minutes at a time. This is why flight testing is absolutely essential, and it's why programs like X-51, X-43, and Talon-A are so valuable. Every test flight provides data that can't be obtained any other way. The good news is that our computational capabilities and sensor technologies have improved dramatically. What was impossible to model 20 years ago can now be simulated with reasonable accuracy. But simulation still needs validation with real flights. Section 6. The Sonic Boom Challenge. Let's talk about an issue that killed Concorde's profitability and threatens to limit supersonic and hypersonic flight. The sonic boom. What is a sonic boom? When an aircraft exceeds the speed of sound, it creates a shock wave, a sudden pressure change that propagates to the ground as a loud boom. It sounds like an explosion or thunder, and it can rattle windows and disturb people over a wide area. Concorde's sonic boom was so disruptive that it was banned from supersonic flight over land almost everywhere. This meant Concorde could only fly supersonic over oceans, severely limiting its routes and economics. For decades, regulations prohibited supersonic flight over land in most countries. As I mentioned, the US just lifted its ban in June 2025, but concerns about noise pollution remain. The hypersonic boom question. Here's the thing, as you go faster, the sonic boom characteristics change. At hypersonic speeds, the shock waves behave differently than at Mach 1 or 2. Some research suggests that at very high altitudes and speeds, the sonic boom might not reach the ground at all, or might be significantly weakened. This is the concept behind boomless cruise, flying at speeds and altitudes where the boom doesn't cause ground disturbance. Boom Supersonic has been researching this extensively. Their XB-1 demonstrator broke the sound barrier multiple times without creating audible sonic booms on the ground. NASA has captured Schlieren photography showing the shock waves around the aircraft during supersonic flight. The key factors are altitude, speed, and atmospheric conditions. Fly high enough and fast enough, and the shock waves may dissipate before reaching populated areas. Shaped sonic boom technology. NASA has been working on another approach, shaping the aircraft to create a softer sonic boom, more of a rumble than a bang. Their X-59 quiet supersonic aircraft is designed to produce a sonic thump instead of a boom, quiet enough that supersonic flight over land might be acceptable. While the X-59 is designed for supersonic, not hypersonic speeds, the research applies to faster aircraft too. The shape of the nose, body, and wings can dramatically affect the shock wave pattern and resulting noise. Practical implications. For commercial hypersonic flight to be viable, the sonic boom issue must be solved. No one is going to accept daily hypersonic aircraft creating massive sonic booms over cities. The lifting of the US ban on supersonic flight is encouraging, but it came with the condition that aircraft must not create unacceptable noise levels. Aircraft will need to demonstrate low sonic boom characteristics to operate over land. Military hypersonic vehicles have more flexibility since they don't fly regular routes over populated areas. But even there, noise considerations matter for training and testing. Section 7. Commercial viability. All the technology in the world doesn't matter if hypersonic travel can't be economically viable. Let's talk business reality. The Concorde lesson. Concorde was a technological marvel and an economic disaster. It cost enormous amounts to develop and operate. Tickets were so expensive that only the ultra-wealthy could afford them. Routes were limited, and only 20 aircraft were ever built. British Airways and Air France operated Concorde at a loss for most of its service life, continuing mainly for prestige. When one aircraft crashed in 2000 and operating costs kept rising, it became clear the economics didn't work. Any future supersonic or hypersonic aircraft must learn from Concorde's failure. Development costs. Developing a certified, commercial hypersonic aircraft will cost billions of dollars. Engine development alone could run to $1 billion or more. Boom Supersonic has raised hundreds of millions and they're only building a Mach 1.7 aircraft. True hypersonic passenger aircraft, Mach 5 or above, would cost even more to develop. This money has to come from somewhere: investors, government contracts, or airline pre-orders. The SR-72 benefits from military funding where cost is less constrained. But commercial aircraft need to show a path to profitability or investment dries up. Operating costs. Even after development, hypersonic aircraft will be expensive to operate. They'll consume enormous amounts of fuel. Maintenance will be intensive because of the thermal and structural stresses. They'll require specialized support infrastructure. For airlines to adopt them, the ticket prices must be high enough to cover these costs while remaining competitive with business class on conventional aircraft. Boom estimates Overture tickets will cost around $5,000 round trip across the Atlantic, roughly comparable to current business class. But that's for Mach 1.7, with technology fairly close to current jets. Hypersonic aircraft will likely command premium pricing, at least initially. You're probably looking at prices comparable to or exceeding first-class tickets. Market size. How many people are willing to pay $10,000 or more to save a few hours? There's definitely a market: business travelers on time-sensitive trips, wealthy individuals who value their time, government officials. But is that market large enough to support an entire industry? Airlines need to fill seats consistently to make routes profitable. The addressable market probably includes ultra-premium business travelers on long-haul routes, government and military VIP transport, time-sensitive cargo and mail, emergency medical transport, specialized corporate and charter services. That's a much smaller market than mass commercial aviation, which means production volumes will be lower and unit costs higher. Infrastructure requirements. Hypersonic aircraft need specialized facilities, longer runways for takeoff and landing, specialized fuel handling, advanced maintenance capabilities, air traffic control systems that can handle Mach 5 aircraft. Building this infrastructure requires massive investment. Who pays for it? Probably a combination of governments, airlines, and aircraft manufacturers. The realistic timeline. Here's my assessment of when we might see commercial hypersonic flight. 2025 to 2030. Continued testing of hypersonic demonstrators. Military hypersonic systems entering service. Supersonic aircraft like Overture potentially entering commercial service. 2030 to 2035. First hypersonic passenger aircraft might begin flight testing. These would likely be small, experimental services on limited routes. 2035 to 2040. If testing goes well, initial commercial hypersonic operations could begin. Think a handful of aircraft serving major business routes. 2040 to 2050. Potential for broader adoption if technology proves reliable and costs come down. But here's the reality check. We've been 5 to 10 years away from hypersonic passenger flight for decades. The technology is advancing, but so are the standards for safety, noise, and environmental impact. My honest assessment? Hypersonic passenger flight will happen eventually, but it will remain a premium service for wealthy travelers and time-sensitive missions for many years, possibly decades. Mass-market hypersonic travel, where regular people fly hypersonic like we fly subsonic today, that's probably not happening in our lifetimes. Section 8. The environmental question. We need to talk about something that's often overlooked in discussions of hypersonic flight: the environmental impact. Fuel consumption. Hypersonic aircraft will burn enormous amounts of fuel. The energy required to overcome drag at Mach 5 is vastly higher than at subsonic speeds. Even if they use sustainable aviation fuel, as Boom's supersonic plans for Overture, the sheer volume of fuel consumption raises questions about sustainability. Emissions at altitude. Aircraft emissions at very high altitudes, where hypersonic aircraft would fly, have different environmental impacts than low-altitude emissions. Water vapor and other compounds released in the stratosphere can affect the ozone layer and contribute to climate warming. The environmental impact per passenger mile of hypersonic flight will almost certainly be higher than conventional flight, at least initially. Noise pollution. Even if the sonic boom issue is solved, hypersonic aircraft will create other noise. Engine noise at takeoff and landing, though electric and advanced engine designs might help here. Development versus operation. Interestingly, one argument in favor is that hypersonic technology development, the testing, the failed attempts, the learning process, produces relatively little environmental impact compared to decades of regular operations. If hypersonic flight remains a niche service for premium travelers rather than becoming mass market, its overall environmental footprint might be manageable. The bigger picture. Aviation currently accounts for about 2 to 3% of global carbon emissions. If hypersonic flight remains a tiny fraction of total aviation, its impact might be negligible in the grand scheme. But if it becomes widespread, or if the testing and development phase involves thousands of test flights, the environmental costs could be significant. This is a tension the industry will have to address, especially as environmental regulations tighten globally. Conclusion. So where does all this leave us? Hypersonic flight is real. It's not science fiction. We have aircraft flying above Mach 5 right now. The SR-72 could be operational within this decade. Stratolaunch is flying reusable hypersonic vehicles. The technology exists. But making it practical, safe, economically viable, and environmentally acceptable for commercial passenger flight? That's the real challenge, and we're probably decades away from solving it completely. What's realistic short-term? Military hypersonic systems entering service in the next 5 to 10 years. Continued testing and development of hypersonic demonstrators. Supersonic passenger flight potentially resuming this decade with aircraft like Boom's Overture. Incremental progress on all the key technologies: propulsion, materials, thermal management. What's realistic medium term? First experimental hypersonic passenger flights in the 2030s. Limited commercial service on a few high-value routes. Continued technology development making systems more reliable and efficient. What might never happen? Mass-market hypersonic travel where regular people routinely fly at Mach 5. Hypersonic aircraft replacing conventional jets for most routes. Ticket prices comparable to today's economy class. The race for Mach 5 isn't a sprint, it's a marathon. The finish line keeps moving as we learn more about the challenges. But progress is real and accelerating. In my view, hypersonic flight will become a reality for specific applications: military reconnaissance, VIP government transport, ultra-premium business travel, specialized cargo. It will transform those niches. But it won't revolutionize aviation for most people. And maybe that's okay. The technologies developed for hypersonic flight, advanced materials, thermal management systems, propulsion innovations, will benefit other areas of aerospace and beyond. The race for Mach 5 is pushing the boundaries of what's possible. That alone makes it worth pursuing. What do you think? Would you pay $10,000 to fly hypersonic across the Pacific? Are we underestimating or overestimating how quickly this technology will mature? Let me know in the comments. If you found this deep dive valuable, hit that like button and subscribe for more in-depth aerospace content. Thanks for watching, and remember, the future of flight is being written right now. It's just being written at Mach 5.